In this video, I'm going to give a quick lesson on compound interest and solve a couple of problems for you. So first, what is simple interest? So simple interest is uh, the, uh, the idea that I need money now. So I'm willing to go to a bank or to a loan shark and enter an agreement where the bank will give me some money now, and say a year from now, I will pay back that money along with some extra money called the interest. The convention is that the amount borrowed is called principal, meaning first amount. Then there's an interest rate, which is usually advertised as a percent, but we generally have to work with it in decimal form. And then the amount of the debt in the future, there's different symbols for it. For right now, I'm going to use A. And the convention is that the um, say a year from now, the amount of the debt will be the principal plus the interest rate R times the principal. And you can factor out the principal and say that the amount in a year will be the principal times 1 plus R. The disadvantage to this kind of simple debt is, well, it's not flexible. So for example, suppose that I needed to make some repairs around my house, make some urgent repairs around the house. So maybe I go to the bank and take out a loan, and we agree that in a year I will pay back the loan plus, say, 5% interest. But then suppose that while I'm working on my house, it turns out that the problem is bigger than I thought and I need to go borrow some more money. Well, if this was the only kind of loan I had available, I would have to take out an all-new loan to cover this additional expense. Furthermore, suppose I later found some money and I wanted to pay back the loan early and not pay as much interest. Well, that's just not possible under this kind of very simple debt. So you don't see this kind of very simple debt done too often. One common example of it is something called a certificate of deposit. It's kind of the reverse of a loan. Uh, you would make a deposit into a CD account at a bank, and then at a specific time, usually either a quarter or half a year or a whole year later, the bank will return your money plus interest. So the bank is effectively borrowing money from its customers through this thing called a certificate of deposit. There are ways of getting around the inflexibility of a CD, but that's how the basic financial instrument works. But since that's kind of a pain, over the years, banks have come up with this system called periodically compounded debt, or compound interest. So the idea is you borrow an amount called the principal. There's an annual interest rate that's usually advertised as a percent, but we generally work with it in decimal form. There's the future value of the debt, and then part of the terms of the debt are that there's some number of compounding periods per year. Very often you will see compounding periods of, say, quarters, which is 3 months, a quarter of a year. You might also see um, monthly, so a mortgage is uh, monthly, and in that case, N would be 12. For quarterly, N would be 4. For weekly, N would be 52. You could also do daily, N would be maybe 365. And then T will be time in years. This formula for the amount of the debt after some time T assumes that you aren't paying back the debt yet. But again, the idea behind having debt like this is that if you wanted to, every compounding period, you could either pay some of the debt off, that's what's done in a mortgage, or you could maybe borrow some more money if that became necessary. And so it's a much more flexible way of lending money. Now, as to where this formula comes from, remember that a percentage calculation, So starting with an amount and then adding a certain percentage to it can be done by multiplication. You multiply by 1 plus the fraction of the principal that you want to add on. The R over N is, again, part of the convention. The advertised rate is meant to be roughly analogous to the interest rate you would pay for a year-long loan. But since it's divided up, since the loan is divided up into smaller time intervals than just a year, the convention is that you advertise this rate R, but you use R over N to figure the periodic compounding rate. Then N times T is the number of compounding periods that have elapsed. If there are N compounding periods per year and T years have elapsed, you multiply N by T to get the total number of compounding periods in T years. That means that you've applied this factor of 1 plus R over N once for each of these compounding periods. So that's where this formula comes from. So here's an exercise that I encourage you to do. Suppose I borrow $1,000 at an annual interest rate of 5%. What is the amount of the debt after 4 years if interest is compounded yearly, quarterly, monthly, or daily? So pause the video and take a few minutes to try this out. Okay, well, I'm going to switch over to the calculator and show you how to make these calculations. Mostly this is a matter of making sure that you have a demonstration of where to put parentheses and things like that. Again, the formula that we're going to use is the principal times a periodic interest rate factor raised to a power that's the number of periods that we're dealing with. So if we're borrowing $1,000 at an annual interest rate of 5%, and we want to know the amount of the debt after 4 years if interest is compounded yearly. Okay, this is really not difficult to do. So there's the principal times, and for yearly, you don't really even need a denominator. You'll just do 1 plus R because the N for a yearly debt would be 1 compounding period per year. Now I need 5%. So remember, we have to make that 0.05. And then since there are 4 years in this problem, I'm going to put a power 4 on that. Okay. So there we go. $1,215.50. The bank would round that to 51 cents. So there we go. That's the result for yearly compounding. Now for quarterly compounding, we'll use n equals 4 in that formula. So here we go. 1,000 times 1 plus, and I'll put in a fraction template just to make this as clear as possible. The 5% goes right there. That's R expressed as 0.05. N is 4 for quarterly compounding. So there's the periodic interest rate factor. Then up here, I need to put in 4 times 4. That's because we're running this debt for 4 years and 4 compounding periods per year, quarterly. So now I'll run it, and you see that it comes out a little different. If you leave everything the same but change the number of compounding periods, then the amount of the debt at the end of the time interval that you're interested in is a little higher. So the more often you compound, the more it accumulates. So that's that's the result for quarterly. If you want to do monthly compounding, again, there's the principal times, and then 1 plus, and I'll put in a fraction template, 0.05. Monthly means 12 times a year. That means n is 12. And now the exponent, remember, is n times t, so 12 times 4. And so there you go, $1,220, and that would round to 90 cents. Let me do one more of these. I'm going to change this calculator back to left to right mode. That's so that if you have a calculator that doesn't have the fraction templates in the two-dimensional layout, that you can see what's going on. So there's the $1,000 principal. Then I need parentheses for the periodic interest rate factor. So that's 1 plus 0.05, and now I'm going to do daily. So I divide by 365. So n will be 365. Now I need to put a power on that. And this is a place where students sometimes make mistakes. I need to raise this to 365 times 4. Let me do it correctly with parentheses around the 365 times 4. Now you can see that's reasonable. The pattern that you should be seeing is that as we adjust the number of compounding periods per year, leaving everything else the same, the amount of the debt after 4 years does increase slightly. $1,200 something dollars is about what we would expect. So if you had mistyped this, let me show you a mistake that students will sometimes make. So if I leave out those parentheses, I get something that's way off. The reason this happens is that what I have typed up here means to take 1,000 and to multiply it by the result of 1 plus this 0.05 over 365 to the power 365, then multiply all of that by 4. And that's not the formula that I want. I need to multiply the 4 by the 365 and use that as the exponent. And that's why you need the parentheses up here. Remember, the calculator is a real stickler for the order of operations. It looks at this power 365 times 4, and it thinks you mean that you want the power 365 applied first to that result of the thing in parentheses, and the multiplication happens afterwards. So just watch for that. What you really want is 4 times 365 all up in the exponent, and on the left to right calculator that requires parentheses. Now that's just a matter of using a formula, and I'm guessing many of you who are watching this have seen that formula before. Let me show you something that you may not have seen before. So suppose I invest $5,000 in a CD that earns interest compounded quarterly. So what I mean by this is that very often the bank will let you deposit money into a quarterly CD, and every quarter, if you don't ask for your money, they just roll it back over for another quarter under the same terms. So a quarterly CD can turn into a flexible investment that uses the same formula as a quarterly debt. I would like to have $6,000 at the end of 5 years. What APR must the account earn for that to happen? APR is the annual percentage rate. So that's the advertised percent, the R that we're trying to solve for. So let's let's take a look at how to solve this. So first, let's recall the compound interest formula. Okay, so there it is. A equals P times a group 1 plus R over N, all to the power N times T. Now let's go back to the problem and see what we need to fill in. Okay, so there's the problem again. What do we do with the 5,000? Okay, the 5,000 is the principal. That's the amount borrowed initially. What do we do with the 6,000? That's actually the end amount of the debt. So in other words, A is 6,000. That's our goal, is to have the account climb up to 6,000. Now what do we do with the 5? In particular, that's 5 years. Well, that is T. So now we have everything except for R and N. Well, where does, where do we, what do we know about N? Right over here, it says that the interest is compounded quarterly. That means 4 times a year. So that means that we need to set N equal to 4. Okay, so N equals 4. And then finally, well, we're asked what APR. That means that the remaining symbol is what we need to solve for. So solve for R. Okay, so let's put all of this together. 6,000 for A equals 5,000 times 1 plus R over 4 to the 4 times 5. Now our goal is to solve for R. This kind of equation can be solved by peeling the onion. I suggest that you take a moment to try to do this and see if you can get it. Okay, peeling the onion, remember, is this technique where you undo one operation at a time. So first, the outermost operation is that multiplication. The part in parentheses happens early in the order of operations. The stuff up in the exponent is grouped as well. The very last thing in the order of operations is the multiplication. That's the first operation we should undo. Okay, and to undo multiplication by 5,000, we can divide by 5,000. So that leads us to here. So 6,000 over 5,000 equals 1 plus R over 4. And I'll go ahead and do 4 times 5 and make that 20. Now here's a part where students are often stuck. The next thing in the order of operations, I need the outermost operation over here. Now that we've gotten rid of multiplication by 5,000, the outermost operation is the exponent 20. Now, how do you undo an exponent? Well, one way to think of this is that you could do a 20th root. But there is a way to do that on the calculator, but it's buried in a menu somewhere. It's usually easier to remember that if you have an mth root of some stuff, that's the same as stuff to the power 1 over m. So what I'm going to do is apply power 1/20th to both sides of this equation. The reason that works is that if you'll remember, if you have stuff to, I'm running out of letters here. Uh, I'll just stick to m and n. So stuff to the m to the n, you can make that stuff to the m times n. So when I simplify on the right, I'll get 1 plus r over 4 to the 20 times 1/20th. On the left, I'll just leave it as 6,000 over 5,000 to the 1/20th. And what's going to happen that's very nice is that since 20 times 1/20th is 1, the exponent there will simplify down to just 1. And a number to the power 1 is, well, it's just the number. So I can actually scratch through this. I don't need to write power 1, and I can simply write that this is 6,000 over 5,000 to the power 1/20th. Same thing on the left there, but now on the right, I've simplified it all the way down to 1 plus r over 4. Now, if you're being very, very careful about this, you'll recognize that we took an even root, and if we really wanted to be fully mathematically correct about this, we would need to deal with the plus or minus issue, because when you take an even root, that introduces a plus or minus. However, we are only interested in the positive 20th root of the 6,000 over 5,000, because the negative one just doesn't make sense in the context of this financial word problem. So luckily, we don't actually need to worry about a plus or minus over here. Now at this point, it should be clear what we're supposed to do. The next operation we have to get rid of is that addition. So I'll subtract 1 from both sides. That leaves us with 6,000 over 5,000 to the 1/20th minus 1 equals r over 4. Now the outermost operation is division by 4. So I'm going to multiply by 4 on both sides to undo that. So that will leave us with 4 times this thing, 6,000 over 5,000 to the 1/20th minus 1, and just r on the right. One thing that I will warn you about, you have to multiply the entire left-hand side by that 4, and because there's subtraction here, you need to put parentheses here and here so that you have 4 times the entire left-hand side. Okay, so what remains is to type all of this into the calculator. If you like, you can simplify 6,000 over 5,000 and cancel a factor of 1,000 and make that just 6/5. That'll save us some typing on the calculator and make things a little bit easier to see. So I'll go ahead and do that. Okay, let's take a look at the calculator. So again, the calculator is currently in left to right mode. I will therefore have to type quite a few parentheses to get this in. I encourage you to pause the video for a minute and try to type all of this calculation in. You can do it in multiple steps if you like, but do give that a quick try. Okay, I'm going to start with 4 times, and then all of the stuff that goes here is the parenthesized expression. So next I need 6/5 to the power 1/20th. Okay, so 6 divided by 5, I need to put that in parentheses because I need to apply a power to a fraction, and without the parentheses, the calculator will interpret that differently. Okay, so I need 6/5 to a power, not 6 to a power over 5, and not 6 over 5 to a power. That's what you would get if you left out those parentheses. So now I need power 1/20th. And here again, you got to be careful. If I type it like this, the calculator will interpret that as do 6 divided by 5, raise it to the power 1, then divide the result of that power by 20. That's not what we want. What we want instead is the power 1/20th. So we need to put in parentheses, so I'll do second and insert to get the insertion cursor, and that lets me put in parentheses right there. And if you were paying attention and typed the parentheses in correctly the first time, that's great. Otherwise, that's how you can go back and add them in. Okay, then minus 1, and now I'm ready to close up the parentheses for that outermost group. So when I hit enter, this is going to give me r equals 0.03663. The problem didn't say, but I'm going to give the answer to 4 significant digits. If you do have a calculator with two-dimensional layout, which is called MathPrint on this one, then things are a little bit easier on the eyes. You can do 4 times. You still need the parentheses. Oop, yeah, that's what I want. This is the 6/5, and then here's the exponent, and I can use another fraction template up in the exponent. Minus 1. And there it's a little bit easier to see that that's been typed correctly, and there it is. One thing to know is that interest rates are usually small numbers, and they're normally advertised as percents because that way you don't have to deal with these sort of small numbers that are just difficult to talk to. It's just a convention. Also, the fact that we're using them, give or take, with some percent addition to formulas, that's why they're generally given as percents. So when you actually give the answer to this question, R is approximately 0.03663. The required APR, which is advertised annual percentage rate, is I need to convert this to a percent. That means I need to multiply it by 100 because the percent symbol effectively gives a denominator of 100. To multiply this number by 100, I'm going to hop the decimal over 2 times. So now 3.663%. Okay, and just to give you some idea of the order of magnitude, typical interest rates might be somewhere between 1/4% and maybe 20%, depending on the situation. So that's oop, that is okay, let me change back. So that is the solution to that problem. Okay. Now, again, going back to our our solution, the steps, you got to be careful with the algebra. You got to be sure you got parentheses in the right place, and you have to know how to undo a power 20 by using power 1/20th, or equivalently by using a 20th root. That's why I generally go over that in the algebra test and the algebra review at the beginning of the semester.